Suppose that we were asked to diagonalize this matrix. Find the eigenvalues and eigenvectors. Of course, we could begin by doing the determinant of A minus lambda times the identity. But this determinant is easy. The 4 minus lambda is the only element of its column. And therefore, I could expansion by minors along the first column. The remaining matrix will be this one, that minor matrix. And that minor matrix has 3 minus lambda as the only element of its column. And therefore, we'll have that. And then there's only one element left. So I have lambda equals 2, lambda equals 3, and lambda equals 4 2 times. All right, here we have an eigenvalue with multiplicity 2. All right? So we only have 2 distinct eigenvalues. All right, well, let's see what happens when we get eigenvectors. Oh, I can have lambda 1. Oh, by the way, we could have read that immediately off of here, because whenever you have an upper or lower triangular matrix, its eigenvalues are displayed prominently on the diagonal. Okay? That's a useful fact to remember. It's very easy to see why it's true, because that was what we used in order to take the determinant here. So I'm going to say lambda equals 3 and lambda equals 4. All right, 3. Remember, you only subtract the eigenvalue from the diagonal. All right? This would ref to would have 4, I would have V1 equals 1, negative 1, 0. There's my eigenvector associated with eigenvalue 3. What about my eigenvectors associated with eigenvalue 4? Well, now I'm subtracting 4 from the diagonal. So I have 0, 1, 7, 0, negative 1, 2, 0, 0, 0. All right, how does this ref? Well, I could do 0, 1, 7, 0, 0, 9, 0, 0, 0. Okay? And notice that I only have one column lacking a pivot. So my general element of the null space of this matrix would be S0, 0. So V2 would be 1, 0, 0. And notice that we do not have an eigenbasis for this matrix. We have only two linearly independent eigenvectors. So for that reason, this matrix is not diagonalizable. All right, it is not similar to a diagonal matrix. So what's the issue? What caused this failure of diagonalizability? Well, we only have two eigenvalues. Every eigenvalue is guaranteed a linearly independent eigenvector. We can prove that shortly. However, what's happened here is that we only get two eigenvalues because the 4 has claimed that it is worth two linearly independent eigenvectors. And then it fails to deliver. All right? These eigenvalues with multiplicity greater than 1 have a name. They are called degenerate eigenvalues. Degenerate eigenvalues. Now, as we've seen here, a degenerate eigenvalue can fail to live up to its claim. All right, if it has multiplicity 3, then it's claiming to be worth 3 linearly independent eigenvectors. It does not have to produce 3 linearly independent eigenvectors. It might fail to live up to its claim. It doesn't have to. It is possible for a degenerate eigenvalue to live up to its claim. That depends on the details of the matrix. In this example, had this number not been a 7, but instead a -2, then the matrix, or the degenerate eigenvalue, would have lived up to its claim. The matrix would be diagonalizable. All right? So if that had been a -2, then let's see what happens. All right? Here I have 2 columns that lack a pivot. And so I would have a V2, but I would also have a V3. All right? 3 linearly independent eigenvectors. The eigenspace associated with eigenvalue 4 is two-dimensional. Stated another way, A minus 4 times the identity has a two-dimensional null space. The dimension of the null space of A minus lambda times the identity is equal to the dimension of the eigenspace of A associated with eigenvalue lambda. So the whole space span of 1, 0, 0, 0, 2, 1 consists of eigenvectors associated with eigenvalue 4. All right? So if I were to take P as that, or notice what I did, I used the eigenvector associated with eigenvalue 3. Then I mixed and matched. I used the sum of these two vectors. Doesn't matter. All right? These can be any eigenbasis. All right? So just like in the last example, we could multiply by 2 or negative 3 or whatever. If I have an eigenspace with dimension greater than 1, I can use linear combinations of my eigenvectors as well. As long as I have 3 linearly independent eigenvectors. So I could say P inverse AP would be, well, it's the eigenvector associated with eigenvalue 3 first, then eigenvalue 4, then eigenvalue 4 again.